In this video, we'll be looking at our PRBL from Friday. Take notes over this video. The notes will be 30% of your grade. Your output, the grid paper you submitted, will be 70%. These notes will be 30%. What should be in the notes? Well, whatever you feel important, but I will highlight some definitions that should certainly be in your notes. Number one, we were asked to construct a scatter plot of male height versus femur length and describe the scatter plot. Here we see the scatter plot, femur length on our horizontal axis, male height on the vertical, and the points appear to be in a perfectly straight line. This data is clearly faked. It's made up. Actual data you'll rarely see to be perfectly linear. So direction, outliers, form, and strength. The direction is clearly positive. The form is linear, and the strength is very strong. It's perfectly linear. If we calculated the correlation coefficient R, it would be exactly 1. As femur length increases, height tends to increase, and that's pretty obvious. Question 2 asks us to construct the same scatter plot but with female height on our vertical axis. And you can see it's also very strong. It's not a perfectly straight line. If you calculated the correlation coefficient here, it would be almost 1, but not quite. Again, direction, outliers, form, and strength. The direction is positive. The form clearly linear. And the strength is very strong. Again, R would be near 1, but slightly less than. R slightly less than 1. Correlation coefficient. No outliers. Problem number 3, we were asked to calculate the regression equation, and using the website that I suggested to you, here you can see our regression equation. It's y equals 81.75 plus 1.875x. This is our first scatter plot, and you can see again these points are in a perfectly straight line. For our second scatter plot, the regression equation was y equals 73.3 plus 1.95x, and you can see that a couple of these points are slightly off of the line, but it's very close to perfectly linear as well. The next question dealt with interpreting slope and y-intercept. Well, this PRBL was essentially working with two main things, linear equations and inverses. And we're dealing with linear equations. One of our big forms is slope-intercept form. Slope-intercept form is the form of the equation y equals mx plus b. M here is the slope. One way we calculate slope is to find a change in y divided by change in x. This symbol here is the Greek letter delta, this triangle-shaped symbol. Think D for difference. The difference in the y's, the difference in the x's. We also talk about slope as a rate of change. For our particular situation, it's a change in y per x per unit x. That's an easy way to interpret our slope. B, this is our y-intercept. It's essentially a point. When x is equal to 0, that value b, that is the y-intercept. So in our particular problem, we had two regression models. I'm going to say y1, our male equation, 81.75 plus 1.875, and our y2, 73.3 plus 1.95. Interpreting our first slope and y-intercept, well, this is the y-intercept. It corresponds with the point 0, and I'm just going to round this to 82. Interpreting this point, keep in mind what our x and y variables are. Our x variable is femur length our y variable is predicted height. So when the femur length is 0, we predict a height of 82 centimeters. This is, of course, nonsensical. You can't have a femur length of 0. That would be no leg. So often when you create a linear regression, the Y-intercept may be meaningless in context. This slope of 1.875, think change in y per unit x. We predict for every 1x, in this case for every 1 centimeter of femur length increase, male height will increase 1.875 centimeters on average. Y per x, change in y per unit x. And in a similar fashion, you could describe your slope and y-intercept of that second line. All right. The other main part of our section was finding an inverse. And this is finding the inverse of an equation. Let's take our particular example here. Our y equals 81.75 plus 1.875x. Again, we should define our variables here, but our x is our femur length and our y is our predicted height for a man, predicted male height. All right. To find the inverse, 3-step process. Step 1, exchange x and y. So we rewrite this equation, changing y to x, likewise x to y. Step 2, solve for y. In this case, if I'm going to solve for y, I'll subtract 81.75 on both sides. Left-hand expression, x minus 81.75. Right-hand expression, 1.875y. Dividing both sides by 1.875, the coefficient of y. We are left with y equals x divided by 1.875. Dividing 1x by 1.875, that is equivalent to the fraction 8 over 15, which if you left it as a decimal is 0.53 repeating. Then 81.75 divided by 1.875 is 43.6. This is our inverse function. In our inverse function, the mapping is reversed. X is now the predicted, X is now the male height. And technically it is our predicted male height. We shouldn't use our regression equation. And Y is our femur length. In a similar fashion, you could solve for Y2. And looking at the papers, most all of you got that part correct. Step 3, which our book talked about and is more important in a strictly algebraic sense than in our linear regression sense, is to use F inverse of X notation. In this notation here, F inverse of X, again, it's read as F inverse, not F to the -1 power. The choice of the -1 power is not accidental. When we take something to the -1 power, it is the multiplicative inverse, so that statement in mathematics does have inverse meaning. In this particular case, we're going to exchange our output variable y with this f inverse of x. So f inverse of x, y is becoming f inverse of x. And our left side expression is now our right side expression. Of course, we can exchange the sides of the equal signs. That's the symmetric property of equality. In this case, we should have had our original function, our original equation written in function notation. And here you can see I've written it here. Here's our original function, f of x. And here's our new function, f inverse of x. They are the undoing of each other. Question 6 says, perform both regressions again. This time switch the x and the y variable. That is, use height as the x and femur length as the y. I'll begin by saying I don't think we had enough time to do either 6 or 7, so I won't be holding that against you as I evaluate your grid paper that you submitted. So 6 and 7 won't count against you, but I'll discuss them briefly. Here's our male regression equation with the variables flipped. What you can see, it is exactly the same as the algebraic inverse. The reason for that is these points lie in a perfectly straight line. If the points are a perfectly straight line and you have a correlation coefficient of 1, the regression equation inverse will be exactly the same as if we switch the x and the y variables. However, for our second equation, for the females, this regression equation is slightly different than the inverse. If you calculated the inverse, you'll see that it's close to this one, but not exactly the same. And that's because our points don't lie in a perfectly straight line. So the big takeaway from this was that the inverse is not exactly the same as just flipping the variables of the regression equation unless it's perfectly linear, which almost never happens with regards to actual data. Actual data does not fall in perfectly straight line, almost never. So last note for your note page, we also performed a linear regression. A linear regression is constructing a model, and by model we mean in our case both an equation and a line, to predict some y given an x. An important note as it relates to inverses: exchanging the x and y variables will produce a different regression equation, and it usually won't be equal to the algebraic inverse. The only time they will be equal is in the very unlikely event that the points are in a perfectly straight line, which almost never happens with actual data. Take these notes, take a picture of the notes, email it to me, and you will get the other 30 points. Your output will be worth 70 points, and the picture of the notes will be worth 30 points. That concludes this video.